Hi, my name is Mehdi Orouji. I'm a PhD student at the University of California, Irvine, and today I'm going to talk about our work in distilling low-dimensional representation with task-relevant autoencoder via classifier enhancement or trace model. Here's my contact information. If you have any questions, please send me an email, and if you have suggestions and feedback, we highly appreciate that. So higher order regions in the visual cortex encode for high-level features in objects, but the mechanism of how this encoding process happens is poorly understood. This is partly because the techniques that we use, such as fMRI, to study these brain regions contain thousands of features. These features contain task-irrelevant information, and in addition to all of that, the dimensionality of the feature space that these regions encode for is probably much lower than thousands of features. So one goal is how to find a lower dimensional representation that this feature space can best explain performed tasks in the brain region. So there are some things in order to take into consideration for that. One is that we do not know the functional form of dimensionality reduction in these brain regions. So we are interested in developing assumption-free models. Another thing that the lower dimensional representation should reflect task-relevant information. In order to see that these information are task-relevant information, we need to be able to recover the original input using non-parametric method. So we can use PCA, which is a dimensionality reduction technique, but it is a parametric method, and it does not guarantee task-relevant information. We can use autoencoders, which is a non-parametric method, but it does not guarantee task-relevant information, or we can use CNN that cannot reconstruct input using encoded information. So that's why we are developing task-relevant autoencoder via classifier enhancement, which is a mouthful, so we call it trace. That is basically an autoencoder, except you are attaching a classifier to the bottleneck to ensure that the encoded features in the bottleneck are task-relevant information. So we have two networks, and we are increasing the dimensionality of the bottleneck from 2 to 1500, and we are looking at how the behavior of these networks changes as a result of change in the bottleneck dimensions. So we have two networks, trace and autoencoder, and we have three data sets, MNIST and fashion MNIST, that are mostly very commonly used in benchmarking deep learning model. And we have the bull signal from ventral temporal cortex that was collected with by another group, that subjects were looking at 40 different categories of objects, and why the bull signal from the ventral temporal cortex from those subjects were collected. So we have four different metrics in order to benchmark trace against an autoencoder. So first one is the reconstruction fidelity, which is the mean Pearson correlation of the input and the reconstruction of each sample. Another one is the bottleneck accuracy, which after the training, the network, in trace and autoencoder, we are using the bottleneck. We are extracting the bottleneck features and using a separate logistic classifier. We are looking at how the classification accuracy changes as the dimensionality of the bottleneck changes. We are looking at the reconstruction specificity, which is looking at the reconstruction exemplars, and we are looking at the mean Pearson correlation within the same class minus between the same class. So we have different instances of zero, and that is, we look at the mean correlation of these different instances of zero, and that is the within class correlation. And we can look at the correlation between zero and all different other classes, that's the basically between class correlation. So reconstruction specificity is the mean of the within class correlation minus the mean of between class correlation. And reconstruction specificity is exactly calculated the same way, but we are using the features in the bottleneck exemplars instead of the reconstructed ones. So here is the four metric and two network and three data sets that I just talked about. I'm going to zoom into the first 250 dimensions because the most interesting part of the thing, these figures, is happening in that region. So as you can see, the reconstruction fidelity doesn't change between the trace and AE, and also the reconstruction specificity doesn't change. That means that the trace model is not losing its ability to reconstruct the input, which is good. Another thing is that the bottleneck accuracy does improve in the trace model, and also bottleneck specificity does improve in trace model, especially in lower dimensions. Therefore, we can conclude that the trace performs much better in encoding lower dimensional task-relevant information in comparison to regular autoencoder, without losing the ability to reconstruct the input from this latent representation. But how else can we understand the trace behavior? Well, one way is to look at the features, encoded features in the bottleneck when we have only two features, and see how these trace network is clustering different classes. As you can see, the trace is doing a much better job in comparison to an autoencoder in clustering different classes, versus the autoencoder, a lot of classes that just are overlaying on top of each other. Another way is to look at the reconstruction of the actual class in the output. We can see that trace model is also doing a very better job in comparison to autoencoder in reconstructing the input. One interesting observation is that because trace is able to encode for more task relevant information in the bottleneck, it is able to reconstruct a canonical or a typical three, even if the different instances of three are different. So we have developed and validated trace, an approach that is non-parametric and can recover original data with no assumptions, can encode task-relevant low-dimensional representation of data with no assumption, can find optimal dimension to distinguish within class versus the between class information, and can do this better than the existing techniques such as PCA, autoencoder, and CNN. At the end, I want to thank you for your interest and listening to my presentation. I want to thank my PI, Dr. Megan Peters, for helping me in this project. I want to thank CFAR for funding this project, and NeuroMatch Conference for providing this opportunity to present our work. Thank you so much and have a great day.